Hello again. This is video lecture 24.1, part 2, where we actually introduce the concept of electrostatic potential difference. But before I do that, I want to go back to the gravitational analog that I was using in the previous video, because I think we're more familiar with gravity and the gravitational force and gravitational potential energy. And I want to talk about a quantity we could have defined last semester if it would have been useful to us pedagogically, and that's the concept that we'll call gravitational potential difference. And then from that, we'll leapfrog onto the electrostatic case. All right, so let's introduce the concept of, make sure I've got the right thing visible, gravitational potential difference. So what we've got is the standard picture of somewhere near Earth's surface. There's the ground. And we've got a uniform gravitational field G arrow directed vertically down. Same quantity everywhere, as long as we stay near the surface. And we're going to take a point mass, a particle, and we're going to move it from one point A to another point B, like so, along any path we want. Maybe we'll bring it along a windy path like that. We'll carry it from A to B in the presence of the gravitational field. So that is its actual path, because we're going to carry it along that. All right. And I know that for that path, in the gravitational field, and the particle has some mass m, I'll draw it at some point, like right there. Right? The particle has some mass m. There's a gravitational force, m times g, and that does gravitational work. W grav. And the formula for that would be F grav dot the displacement, delta r. Let's draw the displacement. That's just an arrow pointing directly from A to B in a straight line. That's the displacement vector, even though the actual path is more complicated. All right, now the F grav on the particle, of course, is vertically down. Right there, the particle. Right, there's the F grav. All right. Now, we could do that dot product, figure out the work. It would depend, it turns out, on the vertical distance, I'll call it h, between points A and B. And in this case, it would end up just being m times g times h. But the point is, we know how to calculate that work. And we know that since the gravitational force is conservative, that work done by the gravitational force can be written as the negative in the change in the gravitational potential energy. So let's write delta U grav is negative F grav dot delta R, or delta U grav is negative M times G dot delta R, where I just used that F grav as M times G vector. Now that's a dot product, G dot delta R, where G, of course, points vertically down, as we know. And we could use that formula to calculate the change in the gravitational potential energy. In this particular case, it would just end up being negative mgh. Even for that complicated, windy path between A and B, it would still just end up being negative mgh. Negative. Gravitational potential energy got less because the particle got closer to Earth's center. All right, so those ideas should all be more or less familiar to us. Now let's introduce a new quantity that we could have done last semester, but just didn't find it that necessary at the time. I want to talk about the gravitational potential difference between our 2 points, A and B, due to our uniform gravitational field, G. Gravitational potential difference. And let's even introduce a notation for it. Difference, delta, V grav. Difference in gravitational potential between points A and B. Defined to be the corresponding change in gravitational potential energy when our particle of mass m moves from A to B, divided by the mass of the particle. Gravitational potential energy difference per unit mass. Okay? That's the definition. Gravitational potential energy difference per unit mass. Now, here's the expression for gravitational potential energy difference between 2 points, negative m times g dot delta r. So what I do is divide that by m. And I have negative g dot delta r. Okay? And the SI unit of this new quantity would be the unit of energy, joule, unit of mass, over the unit of mass, kilogram, joule per kilogram. Okay, so if we can calculate the gravitational potential difference, delta Vg, between 2 points, like A and B, that delta Vg is just determined by the gravitational field, the G. That's what determines that. And if we know what the delta Vg is between the 2 points A and B, then if you come along with your favorite pet particle with mass m, and you want to move the mass m between A and B, it's easy to figure out how much its gravitational potential energy is going to change. That'd be the delta U part. Just multiply the delta V part by m, and you'll get delta U. I'm basing that on this relationship right here. Okay? And we're going to do the same thing in the electrostatic case. We've already talked about electrostatic potential energy change, delta U electric, in a uniform electric field, E. And now we're going to calculate electrostatic potential energy change per unit charge, and call it electrostatic potential difference. That's what we're going to do next. Okay? Electrostatic potential, electric potential. People use both those words interchangeably, but I am limiting myself to the special case of a uniform electric field, like the picture on the right, which I had in the previous video. 2 sheets parallel to each other, flat. One has a positive surface charge density sigma, the other one a negative surface charge density negative sigma. You get a nice uniform electric field in this region between the 2 sheets. And the field points away from the positively charged sheet and toward the negatively charged sheet. Okay? Okay. Now, let's do a thought experiment. Into that field, we're going to put a charged particle, and we're going to have it move from the point labeled A to the point labeled B. Although the path that it actually takes is immaterial. It just moves from A to B. There will be a delta U electric, a change in electric potential energy because of that motion. Okay, and then we're going, and so from that we're going to define the electric potential difference, delta V, between the points A and B. And this electric potential difference delta V is due to, what's the cause of it? That uniform electric field E between the sheets. Just like the gravitational potential difference quantity I just defined, delta Vg, was due to the uniform gravitational field that was there. The electrostatic potential difference, delta V, is due to that uniform electric field E. And the definition of the potential difference, delta V, between the 2 points there, A and B, defined to be, is the change in the electrostatic potential energy of our charge Q as it goes from A to B, divided by Q. So that you can think of delta V as the electric potential energy change per unit charge. Just like electric field is electric force per unit charge, now we have electric potential difference, which is electric potential energy per unit charge. Now, what's the SI unit of electric potential difference? And let me try to be clear here. Note the symbol for this new quantity. There and there. Delta V, potential difference. It's the difference in the electric potential between the 2 points A and B. Delta V. That's the quantity. Now here comes the unit. The SI unit of electric potential difference. Well, it's got to be the unit of energy divided by charge. That's 1 joule per coulomb. Now, in physics, the unit joule per coulomb has its own name. It's its own unit. It's called the volt. So I want to say just a word about names here and symbols to represent quantities. Because there's some things going on here that are a little bit confusing and unfortunate. Okay. We've just introduced a new quantity, electric potential difference, or electrostatic potential difference. Okay, the symbol for the new quantity, electric potential difference, delta V, where that V, when written, is really italicized. If you look carefully at those symbols I've got circled in red, the delta V, the V is italicized, called potential difference. The symbol for the unit of this new quantity, the unit of this new quantity is just a V, nothing else. And that stands for the unit called volt. So there's the symbol for the thing, potential difference, delta V, and then there's a symbol for the unit, V, for volt. The unit symbol is not italicized. That's how you can tell them apart in a textbook. Okay? You would have something written like this. Delta V equals 3V, which looks a little bit odd, but what it's saying is the quantity known as potential difference has the numerical value 3 in the unit of volt. What compounds the confusion here, in addition to the fact that the unit for the symbol, let me say that again. The symbol for the quantity and the symbol for the unit are almost exactly the same. Now here's what makes it even a little bit more confusing. Colloquially, physicists and engineers, especially electrical engineers, will use a different name for potential difference. And you might as well hear it because even I'll probably lapse into using it sometimes. It's so common. The more colloquial name for potential difference is voltage, based on the name of the unit, volt. Okay? So you could very well hear a physicist or engineer interpret that expression I just circled in red as, oh, the voltage is 3 volts. Or, a little bit better, the voltage difference is 3 volts. Although you're more likely to hear them just say the voltage is 3 volts. What they really mean is the potential difference between 2 points is 3 volts. Potential difference is the quantity. Volt is the unit of that quantity. And we really ought to use the names correctly and the symbols. To give you a sense of how silly it really is, it would kind of be like this. When we talk about the mass of something, the symbol is m, we call it mass. The unit, of course, is kilogram, kg. So the symbol for the quantity, m, isn't even remotely similar to the symbol for the unit, kg, nor are the names, mass, kilogram. But we could have said, instead of mass, kilogrammage. What's the kilogrammage of that? Tell me the kilogrammage of that. Would you measure the kilogrammage of that for me? And use the symbol kg for the quantity, as well as the unit. So you report to somebody, yeah, I measured the kilogrammage of that on the pan balance, and it's kg equals 2 kg. That's roughly what we're doing here when we say voltage equals 3 volts. Because we're using the name for the thing and the unit for the thing almost interchangeably, and it's bad usage. Okay? I'm going to try to be good about it and use the proper name for the quantity, potential difference, symbol, delta V. And the unit, volt. All right, now that I've made that point, let's continue. Let's figure out a formula for the potential difference between 2 points in a uniform electric field. Electric field is what causes the potential difference. Let's figure out a formula for it in this case. So for the special case of a uniform electric field, again, I'm thinking of this picture up here with the uniform electric field between the 2 sheets, and you got 2 points A and B. And I want to know the potential difference between A and B in the presence of this uniform electric field. Here's the formula. Delta V is obtained by taking the formula for delta U electric between 2 points A and B when a charged particle Q moves from A to B, and divide by Q. Now, in the video lecture I just made, I introduced the formula for delta U electric in a uniform electric field. Negative Q times E dot delta R. So now I divide that by Q. And I get something that doesn't have a Q in it. And that's the formula for the potential difference between 2 points in the uniform electric field. Negative E dot delta R. And you can use that formula to calculate the potential difference, it would be in volts, between any 2 points in a uniform electric field. And that's what this picture below shows. The picture shows a uniform electric field pointing straight down and a point A, starting point, right there. And now, just because that electric field is there, filling all of space, we can pick 2 points A and B and ask what's the potential difference between those 2 points because of that electric field. Okay? All right, and we're going to use that delta V equals negative E dot delta R. Now let me do the first case in this picture. Let's take the point B to be right over here. Due right of point A. So you can see there the delta R. Straight to the right. But remember the E is straight down. So what do I get when I do E dot delta R? That's a dot product of 2 vectors. Well, that means do negative magnitude E, magnitude dr, cosine of what I'll call phi, where phi is the angle between E and delta R. You see what that angle is? The E straight down, the delta R is to the right, the angle is 90 degrees. For this path right here. And the cosine of 90 is 0. So I get a delta V equal to 0. The potential difference between points A and B is 0. And since the uniform electric field points straight down everywhere, that's true if point B is anywhere on this horizontal line. That means the horizontal line is an equipotential line. Every point on that horizontal line has the same potential value, so that the potential difference between any 2 points on that line is 0. And note that the horizontal line is perpendicular to the vertical electric field, so the electric field vector crosses that equipotential line at a right angle. You've been using that in the lab lately, haven't you? And that's a very helpful thing to remember. Okay? If you're on an equipotential line or surface, then any 2 points on that surface have the same potential, so no potential difference, and the electric field crosses through that surface or line at a right angle. All right, what if I pick a point B instead of being to the right, that point B is to the right and downward some, like that, so that the delta R is like that. Then what can I say about the potential difference between points A and B? In other words, if I were to imagine traveling from A to B, what would be the potential difference between those 2 points? How would the potential change as I traveled from A to B? This formula tells me the answer, except I can't assume it's necessarily 0. Minus magnitude E times magnitude delta R times cosine phi. What's the phi in this case? Well, the delta R is basically like that between A and B, and the E is straight down. So the phi is right in there. Now, I didn't give you enough information to get any numbers, but you can see it there. And here's the key thing about that phi. It's very clear that that phi is less than 90 degrees. And the cosine of an angle less than 90 is a positive number, but then there's this minus out front, so that tells me that as I travel from A to B, the electric potential decreases because the delta V is negative. In this geometry, that's true then for any point B that's below that equipotential line. Any point B below the equipotential line will be at a potential lower than point A. Now, the farther down you go, the lower the potential gets. But all I'm saying is that any point B below the equipotential line has a potential less than that at A. The potential difference is negative if I go down. Okay? Note that going down is basically going with the field. Right? So we can say, for a displacement along the direction of the electric field, even if it's got at a little bit of an angle, right, such the angle between the E and the delta R is less than 90, will result in a delta V that is negative. There's an electric potential difference. What, excuse me, what if the point B is somewhere up here, above point A, so that the displacement vector delta R looks like that? Now what do we conclude about the potential difference as I go from A to B? Well, now the delta R goes like that, points like that, but the electric field points down, so the phi that we have to use is in there. It's very clear that that angle is bigger than 90, and the cosine of an angle bigger than 90 is negative, so the cosine is negative, but there's a negative out front, so the delta V overall is positive. So if you go to a point above the electric field, against the field, the potential goes up. And that's a very handy thing to remember. If you go with the electric field, the electric potential decreases, and if you go against the electric field, the electric potential increases. So that's our first calculation of potential difference between 2 points. It's limited to the special case of a uniform electric field, just because that's easier to deal with, uniform. But let me go ahead and now give you a little bit of an introduction to a situation where I don't have a uniform electric field to deal with. But I'll just talk about electric potential energy right now, and I'll talk about a non-uniform field case. And the most straightforward situation when we have a non-uniform electric field is when I have a point particle somewhere. I'm going to show you a Wiley Plus simulation where we're going to put a charged particle fixed at the origin. It's going to have a positive charge of 1 nanocoulomb. And then there's going to be another charged particle. So that first one will be Q1, fixed at the origin. Then there'll be another one, Q2, that's going to move in the XY plane from point A to point B. Okay? So that second particle, particle 2, is going to be immersed in the electric field of particle 1. And since that's a point particle, its electric field is not uniform. It gets weaker as 1 over r squared, right? All right, so let's go over to Wiley Plus. And now you're looking down from above on the XY plane. And you've got particle 1 fixed at the origin, Q1, and I'm telling you it's 1 nanocoulomb. And particle 2, maybe a little hard to see it right now, but it's right now at point A, which happens to be 2 meters from the origin along the x-axis. And we're going to want to move, we're going to do it ourselves, we're going to move particle 2 from point A up to point B. See where point B is? It's at a radial distance of 6 meters at an angle of 45 degrees from the x-axis. So we're going to move our particle 2 from A to B. It will be moved while it's in the electric field of particle 1. So particle 2, with charge Q2, will experience an electric force from the field of particle 1. And that force on 2 would be Q2 times E, where the E is the E from 1. But 1 is a point particle, so its electric field is Q1 over 4 pi epsilon 0 r squared. And here's the thing. This simulation is going to calculate and show us the work done on particle 2 by the electric force as we move particle 2 from point A to point B. And I want us to observe how much work that is. So here we are with particle 2 initially at point A. And if I hover my mouse over that big brown arrow you see right there, you'll see it shows that that's the electric field at the location of particle 2. That field is due to particle 1. That's the field that particle 2 is immersed in. And therefore the F electric of particle 2 is Q2 times that E. So the electric force on particle 2 is straight out on the x-axis right now. Okay, I'm going to adjust the location of particle 2 with these sliders and move it from A to B. First, I'm going to increase the radial coordinate from 2 meters to 6 meters. As close as I can get. If I can't get close enough, I can always just go in here like this, do a little adjusting. Boom, I've got it at 6. Okay? All right, and that got particle 2 to where you see it. Now I'm going to increase the angle by 45 degrees. See how I'm going along there? Look at the W electric. See it down, see up there? Basically 6 nanojoules. Notice how what's happening to that as I go along the arc. Nothing. The work. Nothing is happening. No work is done as I move my particle 2 along this circular arc. Notice that wasn't true back here. Go back to initial location. See it? Okay? And let's increase. Let's go out radially. Look at the W electric. As I do this, it's getting bigger and bigger, isn't it? So there's work done there, but not along the angular motion. Do you see why not? Why is there no work done on our particle 2 by the electric force along this arc until we get to B? The reason is that the force on particle 2 is radially away from the origin, but on the circular arc, the displacement is tangential to the circle, and the angle between the displacement and the force is 90 degrees, and you have to do F dot ds to get work, and the angle there is 90. Cosine of 90 is 0, no work. All right, so we see then that as we move particle 2 from point A to point B, first going out radially along x, and then going along tangentially along the angle, I have 6 nanojoules of work. All right, now let's move the particle back to the starting point. Just cheat. Okay? And I'm going to move it again from A to B, but now I'm going to take a different path. This time, I'm first going to swing out along the angular part. Notice the work. None. Till I get to about 45 degrees. Well, what I want is exactly 45. There we go. And then I increase the radial coordinate from 2 meters to 6 meters. There's where the work is happening. And look how much work was done. The same as before, 6 nanojoules, even though I took a different path. In fact, set it back, you can go from A to B along any path you want. Any path at all. I can go out a little bit radially, then go a little bit along an angle, then go out a little more radially, and a little more along the angle, and then a little more radially, and a little more along the angle, and a little more radially. You can get the point, and a little more along the angle. And no matter what, look how much work is done. The same. So what I'm showing you is that the work done by the electrostatic force of one point particle on another, which is not a constant force, not a uniform force, is still path independent. So let's now go back to our OneNote, okay? And we can even work out the formula for it. I'll give you a little kind of a crash course in how to do it, but I've got the result right here. You have to do the integral of F electric dot ds from point A to point B. But it really only matters when you go out straight out along the radial line. So when you do that integral to get W electric, you just take F electric times a little step size dr from the distance at point A from the origin, RA, into RB. And then you have integral Q1, Q2 over 4 pi epsilon 0 r squared dr from RA to RB. You bring the multiplicative constants out front. Q1, Q2 over 4 pi epsilon 0. Integral from RA to RB of dr over r squared. And then that's Q1, Q2 over 4 pi epsilon 0. Integral from RA to RB, r to the minus 2 dr. And then just use the general integral x to the n dx equals x to the n plus 1 over n plus 1. So you got Q1, Q2 over 4 pi epsilon 0, where the n is negative 2. So n plus 1 is negative 1. So I have r to the n plus 1 over n plus 1 between RA and RB. That's just negative Q1, Q2 over 4 pi epsilon 0. And r to the minus 1 is 1 over r. And then put in the limits. 1 over RB minus 1 over RA. And then distribute that negative that's out front through. It reverses the RA and the RB. And you get this formula right up here. Q1, Q2 over 4 pi epsilon 0 times 1 over the starting distance between the charges, RA, minus 1 over the final distance, RB. And it's path independent. W electric is path independent, even for a force due to a non-uniform electrostatic field. So that means we can define the electrostatic potential difference, electrostatic potential energy difference for a particle of charge Q2 moving from A to B in a non-uniform electrostatic field due to another fixed particle of charge Q1. Delta U electric will be defined to be negative W electric. So just take the answer for W electric and slap a negative sign in front of it. And it looks like this. Delta U electric equals Q1, Q2 over 4 pi epsilon 0 times 1 over RB minus 1 over RA. Please note what this applies to. Two particles, and the distance between them has changed from a distance RA to a distance RB. Now, it's quite common in the two charge particle situation like this to do the following. Remember, with potential energy, there's a reference point that we pick, and at the reference point, by definition, the potential energy value is 0. Let's do that here. Let's take the final position, point B, to be way out at infinity. Okay? RB is infinitely far away, and we define the potential energy, electrical potential energy associated with these two charges to be 0 at that reference point, because they're infinitely far apart, so their interaction is negligible. So you take the formula for the delta U electric, that's that, right? U electric final minus U electric initial. And for the U electric final, you put in 0. That's this. And for the RB, you put in infinity right there. And to a physicist, 1 over infinity is a 0. Then what you've got is, once you cancel negative signs, U electric equals Q1 times Q2 over 4 pi epsilon 0 R. That's the electric potential energy for two point particles. Okay, we hadn't talked about that case yet in this chapter. And here it is again. U electric equals Q1 times Q2 4 pi epsilon 0 R. That's the electric potential energy of two particles with the reference point at infinity. Meaning when the particles are infinitely far apart, by definition, their electrostatic potential energy is 0. And here I made a graph of U electric. It happens to be in millijoules versus R in meters by plotting that very function. But I did plot it for two cases, because the sign of the U electric depends upon the sign of Q1 times Q2. And charges can be negative. If both charges are positive, or both charges are negative, then Q1 times Q2 is positive, and the U electric function is positive. So when I graph it, I get this hyperbola that's in the positive quadrant. Two particles of the same type of charge. Point being, as the R gets smaller, the U electric gets bigger, more and more positive. That basically means the two particles don't want to be close together. But what if one of the particles is positive and the other is negative? Then Q1 times Q2 will be a negative number. And the actual plot of U electric versus R will be the curve down here on the negative side of the energy axis. Negative potential energy. Yep, you can have that. And now, as the R gets smaller, that potential energy decreases, goes more and more negative. They like that. Opposite types of charge want to get close together. All right, so now we've introduced the concept of electric potential energy for two-point charges. And argued that we're allowed to do that, not by a formal proof, but by more a plausibility argument, and showing you on the simulation that the work done by the electrostatic force in that case is path independent. And that's why it's okay to talk about a potential energy function. Okay, so we'll be talking a lot more. Now, next step will be to go back to electric potential, which remember is potential energy per unit charge. But right now I'm just talking about potential energy. And so let me leave you with a little class engagement exercise that you can do on Blackboard. Okay? Work and electrostatic potential energy. And this is really practice with ideas from both of the video lectures, part 1 and part 2. All right, in this figure, we move a charged particle. Well, it's either an electron or a proton from point I to point F, and that happens in a uniform electric field E, and the particle starts and stops from rest. See the electric field? It points to the right. It's uniform. You see our particle? It's going from I to F, going to the left. Okay? All right. We are to determine and state the signs, positive or negative, of the work, W electric, done by the field, the work W applied, done by us, as we move the particle from I to F, and the change delta U electric in the electrostatic potential energy for the two types of particles. We've got a table to help us organize. We've got an electron and a proton. So first do the case of, say, it might be easier for you to do a proton. That would be the third column on this table. So the proton is moved from point I to point F along that path in that electric field, uniform electric field. You are to fill in with either plus or minus signs. The sign of W electric on the proton. The sign of the work done by your applied force as you move the particle from I to F. And the sign of the delta U electric of the proton as it moves from I to F. Then fill in the middle column, which is where you take an electron from I to F. Is the W electric positive or negative? Is the W applied positive or negative? Is the delta U electric positive or negative? Okay? All right, so that's going to be your class engagement. Okay? And we will be talking about electric potential in our class time on Friday. That's all, though, for this video.